In this lesson, we're going to take a look at equilibrium calculations part 2. And in this type, what we are doing is we are given the equilibrium constant for a particular reaction, and we're asked to find the equilibrium concentrations. So you'll recall that type 1 was one where you are given equilibrium concentrations and you had to find the Kc. So essentially they're opposite to one another. We're going to work through 3 different examples in order to help you to solve this type of problem. The reason we look at 3 different examples of the same type is that there is some different math that we need to use in order to solve the different types of reactions. So the first type is headed taking the square root, and you'll see why as we move through the problem, why it's titled taking the square root. So in this reaction, we are given the concentrations of H2 and Cl2, and so we need to set ourselves up an ice chart here. So the concentrations of H2 and Cl2 are 0.250, and the initial concentration of HCl here is 0. So if we want to complete our ice chart here, we know these are going to go down by x, and this is in turn going to go up by 2x. So at equilibrium, the concentrations of H2 and Cl2 are both equal to 0.25 minus x, while the concentration of HCl is 0 plus x, or plus 2x, sorry, or 2x. So in this type of problem, we're given the equilibrium constant, and we're asked to find the equilibrium concentrations. So what we need to do is solve for x. And we're going to do that by plugging into the equilibrium law, the equilibrium concentrations in terms of x, and then we're going to do the necessary math in order to solve for x. So in this case, the equilibrium constant is 2.51 times 10 to the 4 as given in the question. The concentration of HCl in terms of x is 2x, so we're going to plug the information in from the equilibrium row of our ice chart. Now with these ones, because it's 0.25 minus x and 0.25 minus x, that's really the same as 0.25 minus x all squared. So when we get to this stage, always in these particular types of problems, what we're going to do is make a decision as to what kind of math we need to do in order to solve it. So in this case, we look at the right-hand side and we see that this is a perfect square. So you're always going to look to see if this expression is actually a perfect square. If it is a perfect square, we can simplify the math by taking the square root of both sides. So what we're going to end up doing is getting rid of the x squared term. So rather than having a quadratic to solve, we're going to have just a linear system to solve. Now, when you take the square root, you need to make sure that you do take the square root of both sides. So be careful of that. Okay, so when we take the square root, we get 2x over 0.25 minus x. And so now what we can do is solve for x here. So we're going to move this whole expression over, and then we're going to expand and simplify, and that x value is going to be equal to 0.247. So it's really important that you're able to do the math with these, and this is the biggest challenge for most people. So you need to, I'd recommend that you pause the video at this stage and make sure that you know how to get from here to this x value. Now we haven't actually answered the question yet. We've just solved for the x value. But we can use that x value to now answer the question, which is to determine the equilibrium concentrations for the reactants and products. So I'm going to plug this in. So my concentration of H2 is equal to 0.250 minus 0.247. And this is also equal to the concentration of Cl2. Now for significant digits here, we had 3 in the question, so I found my x value and reported it to 3 for now. But then when we do the subtraction here, we have to remember that when you're subtracting, you're going to use the decimal places as your guide for reporting the correct number of significant digits. So the concentration of HCl is 2 times 0.247, and that's equal to 0.494 molar. So that's how we solve this particular problem. So this next type you'll see is named using the quadratic formula. So you're going to use the information from the question to set up an ice chart. Okay, so you need to be very comfortable setting up these ice charts. So it wouldn't be bad to pause the video and make your own ice chart and then come back and make sure that you're generating an accurate ice chart. Okay, so same thing, we're given the K value. The K value is equal to 85, and we need to sub in the equilibrium concentration. So this is x times x, which is x squared, and then in the denominator we've got 1 minus x times 2 minus x, because it's the concentrations of the products over the reactants all multiplied. So in the previous example at this step, we decided that we could take the square root. This particular reaction does not give such a scenario where we could take the square root. So what we actually need to do is solve this, and we're going to solve it using the quadratic. So the quadratic formula is used to solve a quadratic that's in the form ax squared plus bx plus c is equal to 0. So we need to rearrange this and expand it and simplify it so that it's in this form. And then we'll use the quadratic formula, which you'll recall is x is equal to minus b plus or minus b squared minus 4ac all over 2a. So I find it easiest to always clear the fraction, so move the 1 minus x times 2 minus x over. Okay, and then we need to FOIL this. So we're left with 85 times 2 minus 3x plus x squared is equal to x squared. And then when we expand this, we get 170 minus 255x plus 85 x squared. And I'll move this over, minus x squared is equal to 0. So we're left with 84 x squared minus 255 x plus 170 is equal to 0. So this is what you need to use to sub into the quadratic formula. And when you sub that in, you're going to get 2 different roots. And that's always the case. So you find both the roots. And what you're going to do is decide which one is valid. So again, for your own practice, it would be a good idea to pause the video and determine the x values yourself and then verify with mine. So these are the 2 roots that we found, And what we need to do is decide which one of them doesn't make sense. And we do that by looking back to what the equilibrium concentrations are. The equilibrium concentration of SO2 is 1 minus whatever x is. So if we look at our choices for x's, it is actually impossible for x to be equal to 2.04. If we used x equals to 2.04, we would find that we'd get a negative concentration for the SO2 and the NO2, which doesn't make sense. So that's the kind of chemistry that you need to use in order to disregard one of the roots. Once you've got the roots, you can then plug back in. And I'm just showing you another way that's appropriate for you to report your answers. Okay, you can simply fill them into the ice chart here. Mine's a little bit squished, but if you've got enough room, the biggest thing is to make sure that you include units if you do it that way. Okay, so those are the equilibrium concentrations of all the reactants and products. We've got one last problem to do, and this one is called using the approximation. So we'll talk about how this works once we've set up here. So we've got a reaction that's a dissociation of I2 molecules into I atoms. So there's the equilibrium reaction. And we've got a concentration of I2 initially at 0.200. So our I concentration is equal to 2x at equilibrium. And our I2 concentration is 0.2 minus x. So we can sub into the equilibrium law. Okay. So at this stage we can't take the square root because it's not a perfect square. So we could use the quadratic. We could expand, simplify, rearrange into the form ax squared plus bx plus c equals 0 and use the formula. But because of the size of Kc, we can also take a bit of a shortcut here. The shortcut is that the equilibrium constant is very small, and we're going to define small as being 10 to the minus 5 or smaller. Now what happens here is because the equilibrium constant is so small, we know that that means that the reaction does not proceed very far to the right. So the reactants are very much favored at equilibrium. Because it doesn't go very far to the right, only a small portion of the I2 will actually change. So what we expect is that x is going to be very, very small. And what we're going to do is we're going to make an assumption that because x is so small, when we subtract x from 0.2, really what we get is approximately equal to 0.2. So we want to be careful here. We're not making the assumption that x is 0. We're making the assumption that x is so small that when we subtract it from 0.2, it doesn't change the value by very much. So for example, if you want to plug into your calculator 0.2 minus 0.00001, a very, very small value for x, what you'll see is that if you round it, you're really just going to get 0.2 because you'll get 0.19999. So because we can make this assumption, what it's going to do is take out the x term. And so we're left with 4x squared is equal to 0.2 times 3.8 times 10 to the negative 5. Okay, so if we divide this by 4 and take the square root of it, what we get is that x is equal to 0.00138. the concentration of I is equal to 2x is equal to 0.0028 molar, rounded to 2 significant digits because of the question. Now, in order for this assumption to be valid, what needs to be true is that the change needs to be less than 5% of the initial. So you're going to find the change over here will be 0.00138 over 0.2 times 100. Okay? And what you'll find is that that's less than 5%. And so therefore the assumption is valid. That concludes this lesson in equilibrium calculations.